And I just want to go a little bit more into detail what we have done last time. And I told you we have the general rate equations for things. So, for example, if we have a reaction A, I think we used M or something like that, but it doesn't matter. A reacts into something, A is consumed, we can write the general rate equation. And the rate equation looks usually dA over dt equals plus or minus, in this case, minus. Why minus? Because it's consumed, exactly. Minus a rate constant K times the concentration of A to the power of something. Let's call that M. And I want to say a little bit about M, what M is. M is called the rate order. And this rate order is, if you like, doesn't really have a concrete meaning. It simply is a mathematical concept. Rate order is a mathematical concept. Which allows us to formulate this equation. This rate order can be basically anything. It can be a negative number. It can be a positive number. It can be a whole number. It can be a fraction. So this rate order can be anything. It can be zero, as we discussed last time for a zero-order reaction. It can be plus 155.3. No problem with that. In contrast to the rate order, we also have the concept of molecularity. And molecularity actually means how many molecules interact or are involved in the slowest step of the reaction. The slowest step, that's usually also referred to as the rate limiting step. Now, just a quick question. What number would you expect? Can it be a positive number? Yeah? Okay. So this can be a positive number. Can it be a negative number? You can't really have a negative number of molecules. Minus 2 molecules. Bit weird. So it can only be a positive number. Can it be a fraction? Not really. You can't have half a molecule interacting or doing something. So it has to be a positive whole number. And we are usually talking about molecularity of 1. That is when only one molecule is involved in the process. So, for example, we have radioactive decay, and a molecule just disintegrates. Or we have 2 molecules bumping into each other. We have 2. So, molecularity 1 or 2. Can we have 0? Molecularity 0? So sort of a philosophical concept. If you don't have any molecule to react or to be involved, then nothing happens. So in a way, you could have a molecularity of 0, but then nothing happens. There's no step. So by definition, we don't have 0. We only have 1 and 2. Theoretically, you can have a molecularity of 3, but as far as I know, only one reaction is known where there is a molecularity of 3, and that is extremely exotic.
What is that reaction?
Good question. I don't know. It is with, I think, you probably can Google it. I think it was something of superheated boron reacting with hydrogen and a metal complex or so. But if you find something, put it on Facebook then, or on Twitter. Okay, so we have molecularity and we have order of a reaction. And you see, these two things are something completely different from each other. Okay, so we did the 0 order reaction, and I showed you for this reaction, if we have got that, so 0 order. We have the equation that I want you to remember, A final minus A initial equals minus K times T final minus T initial. And usually this T initial is set, this is the starting point, usually, but not always. And I've put some videos on this first order kinetics assessment. We usually can set this to 0. And that's our starting point. So we have A final minus A initial equals minus K times, and we usually are a bit lazy, we'll just simply say T. And from this equation, we can basically do quite a bit of calculations. But we can also plot this equation. What we can do is we can convert this, the lower one, we can convert that into, so this one here, we can convert that into a straight line. How are we do that? Well, we just bring A initial to the other side, and we have A final equals minus K times T plus A initial. Yeah, just brought the A initial with the other sign, with the opposite sign to this side here. And, of course, this is a straight line. Why? Well, we can write this as y equals mx plus c, which is our lovely equation for a lovely straight line. So we can do that. What do I plot on the y-axis? That would be my A. On the x-axis, I plot time. Now, the y-intersect would be, that's here, that would be my A initial. Line goes up or down? Loud? Down, exactly, because we have minus. So we have something like that. And the gradient of that would be obviously minus k. And that would be the graph for a zero-order reaction. We plot A versus time. Gives us a straight line. And I'm a poet. A versus time gives a straight line. Zero order. Just a quick thing about this K guy. K is a constant. And K is always positive. A negative K is not really, you can't really imagine that. So K is always positive. If you've got problems with remembering that, there's a very simple mnemonic. Did you have lessons with Dr. Foster? No? Not yet. Oh, okay, then forget the mnemonic. Because her first name is K, and she's always very, very positive. So that's how I remember it. K is always positive. But obviously, if you haven't encountered her so far, then don't worry, you will. So K is always positive. And we will come back to the units of K. Okay, so that was the zero-order reaction. Now, we also have, I also showed you the first-order reaction. First order. And, well, again, we have A is consumed. The rate equation for this would look dA over dt equals minus k times A, and this time it is to the power of 1. That is why this one is called a first order. And I showed you that the solution to that is a little bit more complicated. It would be ln A final minus ln A initial equals minus k times T final minus T initial. And again, that is an equation that I want you to remember. Now, there are these ghastly, horrible ln's in it. And I'll show you in a minute how we get rid of them. But first of all, we can convert that into a straight line. So what we do is we just bring this one here, this minus ln, A initial, to the other side. We say this T initial is 0 again. So we get ln A final equals minus k times T, because we said that's 0, plus ln A initial. Yeah? Straight line. Even with an ln in it. Y equals mx plus c. So, what do I plot where? X-axis. What do I plot? Time, exactly. So nothing has changed. I always plot time. What do I plot on the y-axis? I plot the ln of A. Yeah? ln of A. And here comes the bummer. If you've got an ln on an axis, you cannot have units on it. So if there is ln, no units. At least not on this axis. On the time axis, of course, you have unit of, say, minutes or something else. But nothing on the y-axis. I do not want to see units. This is where most people in an exam fall down because they feel the pressure of putting units down here. Don't. Units is not good in this case. What do we get? Well, this point here, that is the y-axis intercept. What is that? ln A initial, exactly. Yeah? We get a straight line. Does this straight line go into the, can it go into the negative range? Who said yes? Yes? Who says no? No? Interesting. Actually, we have ln A final. That is what this line actually indicates, isn't it? Now, if we have, for example, ln 100, what value would that be? Can anyone do that quickly on a calculator? What is ln 100? I don't know by heart. ln 100? 4.6? Okay, I believe you. What is ln 1? Loud? 0. What is ln 0.1? Could we have an A final? That's our A final. Could we have an A final of 0.1? Is that allowed? Yeah? So what is ln 0.1? Negative 2. 2.3. So actually, it can go into the negative range. So if you see it in the negative range, for a lot of people it is, panic, help, mommy. Don't panic. It's fine. Can go negative. With a 0 order, it can't. Because here we have A final, not ln. We have A final, and a negative A doesn't make any sense. Yeah? Makes sense? So, however, if we have, for example, a reaction where we don't know whether it is a 0 or first order reaction, what we can do is we can plot these reactions. So let's say I've got some data here, and I want to know, is this a 0 order or is it a first order reaction? So what I do is I take the data, so I have my time, and I have my concentration of A, and I do my first attempt. So if it is a zero order, I plot time versus A. With my data. And if I get a straight line, I know it is a zero order reaction. There's no other way that I would get a straight line unless it is a zero order. So if I get that, tick box. I know it's zero order. If I plot these data, A versus time, and I get something like that. Straight line? No, not really. Although there are some specialists, especially in exams, who tell me that from this graph you can see it is a zero order reaction. Huh? What? Should have gone to Specsavers. There's no straight line. It's a curved line. If it is a curved line, I know it cannot be a zero order reaction because a zero order reaction would give me a straight line. So what do I do next if I see a curved line? Well, I take my data, and instead of A versus time, I plot ln A versus time. And this should give me a straight line. If it does give me a straight line, I know it is a first order. Sorry? If the zero order gives a curve, then I go to the next step, plot ln versus time. If that gives a straight line, it must be a first order reaction. If it doesn't give a straight line, there are a couple of options. Either you have messed up, option number 1. Option number 2, I have messed up with the data. Option number 3, it is neither a zero nor a first order reaction. It could be, for example, a second order reaction. And for a second order reaction, very briefly, although I don't think you really need to memorize that, a second order reaction, if we have something like that, A plus B gives something, with our methods, we can't solve that. It's a very complicated equation. If, however, it is A plus A, so two components, same components, react with each other, this would probably be molecularity of 2, and it's also order of 2. We can write it as dA over dt equals minus k times A, and the order would be 2 in this case, so it is a second order reaction, but it's a special case where two components are the same. And the equation for that would be 1 over A final minus 1 over A initial equals plus K times T final minus T initial. I don't put a box around that because unless I'm suffering from really bad depression, I'm not going to ask you that. Okay? Happy with that? Now let's go back to the first order reaction. And I said we have ln A final minus ln A initial equals minus K times T. Now I want to calculate, actually, with my Maltesers. You remember last time I had 100 Maltesers, and I said I can eat 10% every 2 minutes. How many Maltesers are left after, say, 5 minutes or so? Now, I really want to calculate A final. But it's with this horrible ln's in there. Yikes! Don't like that. So what can I do? Well, I can rearrange this equation. I can, for example, say ln A final divided by A initial. This is exactly the same as this expression here. It's just simply the rules of logarithms. So you first calculate A final divided by A initial, and then you ln it. Equals minus K times T. Well, okay, fine. But that still doesn't help me a lot, because I still have this ghastly ln in it. How do I get rid of an ln? Loud? E. Exactly. I E both sides. That's E. Remember, E is 2.718 something dooby dum dum dum. So I E the left-hand side, E ln A final over A initial, and I put that in brackets, equals E to the power of minus K times T. And here's where the magic starts, or if you like, where it ends. E and ln cancel each other out. And what we have left is A final over A initial equals E to the power of minus K times T. Or if I really want, I can get the A initial out, bring that to the other side, and I have A final equals A initial times E to the power of minus KT. Now this equation here, this guy, is exactly the same as this equation here, which is exactly the same as this equation here, just a bit rearranged. So if you are familiar with this rearranging, you only have to learn one equation. It is even better than Aldi, because you get 3 for the price of 1. Yeah? You learn this equation here, and you get this one and this one for free. How cool is that? Nobody should say that I'm not good to you. Get 3 equations for the price of 1. I think this is £9,000 well spent. Okay? So, I want you to look at this exercise that's up on Facebook and via email that I sent that around. I want you to do that by Tuesday. Yeah? And this afternoon I will post the assessment for the personal development planning. And this will be in by Monday, the week after next. Have a lovely weekend.